Okay, today guys, we're going to start into vectors. So possibly in your physics class, you guys talked about some of these. So some of the notation will be really close to the same. There's some things that I wasn't able to do on the computer, like put little arrows on everything. So wherever you see these lines, it actually is supposed to be like a ray. That was a bad one. But it comes out to vectors, okay? And vectors, guys, there's a couple different things. There are things that are vectors, and then there's things that are not vectors. Some of the things that are not vectors, we call those scalars. And scalars, remember, or if you don't know, it's just something, it's a number that can describe a quantity. Or it describes a quantity. So when we talk about length, mass, temperature, energy, we just throw a number out there. It's 57 degrees out going to be today during that pancake run. And so it's going to be a beautiful day. But 57 is just a number. It's describing a quantity or something that's out there. I weigh 90 kilograms. So maybe I have a mass, right? So things like that. Those are scalars. Scalars are kind of our numbers. Vectors, though, now the book, I'm not really fond of the definition that the book gives. That's why I'm going to show you guys a video clip in a second. So, a line segment, they say, it's a line segment with an assigned direction. Which is kind of funny because it didn't say anything about having a designated length or magnitude. It just says it's a line segment. But we know if we call it a line segments start and stop. So it's not a line, it's a line segment. So we have a line segment with an assigned direction. And so if point A is the initial point and point B is the terminal point of the vector, then you would call it vector AB. And that would be denoted with AB with a arrow of it. It's kind of like a ray, right? Like almost like ray AB, but it doesn't go on forever. It will eventually stop when we're talking about vectors. Then we can also talk about the magnitude of our length of a vector. And we denote that by putting absolute values, just like we found the modulus the other day. The modulus of something that was in complex standard form or in trig form ended up being the distance or the radius, right? So the magnitude of a vector is its distance or its length. The book will use bold-faced letters to denote vectors. So a bold-faced U is equal to vector AB. So get used to the fact that they're going to start switching from vector AB to just vector U, vector V, vector M, or N, or something like that. And it's kind of interesting that two vectors are considered to be equal if and only if they have equal magnitude, length, and the same direction. So on the bottom here, we're all going to assume, I'm going to be able to draw this very well here, but let's just say that vector is right there. That is the same, or equal vector there, as an equal vector there, an equal vector there, an equal vector there. All of those we can consider to be equal vectors because, not because they're starting and stopping at the same point, it's because they have the same direction, give or take about 45 degrees, and they have a length of whatever. So we're assuming those are all the same, angle and direction. And so the next one actually starts leading into the next step. So I'm going to stop here, and we're going to show a little clip from this big old me about what a vector is. Now that we saw what a vector is, guys, we talk about vectors. We can talk about displacement, basically the movement from your initial point to your termination point. And if we talk about the displacement of vector u being from A to B, and we follow that displacement by vector v from B to C, then the resulting displacement actually is itself the vector that will go directly from the first initial starting point all the way to the ending point of the second vector. Basically, we're going to stack them. And I'm going to show that on the next slide. So basically, start at A, you will end up at C. Well, there's one way to do that, is to follow both vectors independently when you stack them next to each other. Basically saying, I'm going to take the second vector and apply it at the end of the first one. Or I can start at A and walk straight to C. That's where you're adding your vectors together. So it kind of follows this diagram below. So there's a couple different ways. So the sum of vectors, again, is just adding the vectors. You basically are creating the vector from A to C. That's kind of what we were talking about there. And there is such thing as a zero vector, guys, denoted by 0. That might have to, maybe that should have been boldface, I'm not sure. Basically, there's no displacement. If you have a 0 vector, there's no magnitude and there's no direction. Maybe it could be a direction, I guess. It's just that there's no magnitude, because the absolute value of 0 is 0. So that'll kind of play into there. Now, if I wanted to add vectors by sketching, there are two options here. The first option is to literally take vector u and apply it, right? And then take vector v and start its initial point at the terminal point of u and apply its magnitude and direction, which means I could end up here. What that is it creates, so I can essentially call this A, B, C, and so vector A, B added to vector C, B, C will eventually lead me to a new vector from A to C. So you can take the long way to get there, or you can take the shortcut, which is your direct flight, right? Now there's another option, option B there, that says that if you end up having, say, 2 planes or 2 people starting in the exact same spot here, and one person takes the path of V and the other person takes the path of U, and you wanted to add up their things, like how far do they travel together and that type of thing, what you have to do is just kind of make parallel lines to the U and to V, and the point of intersection of those parallel lines creates AC, or U plus V. Okay, so there's 2 different visual representations of getting to the exact same point. One, you're kind of stacking them. The other one is you're doing them independently and finding out what would happen if I still added those components. So there's got to be a way to add some of this stuff. And guess what? We've done this before when you guys have had complex standard form. And so, what we're going to do is we're going to switch it to a form that's a little bit easier than having this using our array or vector AB, and we're going to change it to a form that's component form of a vector. And the component form of a vector is found by taking your initial point and terminal points and subtracting them. And we always like to do final minus initial, or terminal minus initial. Basically, guys, what's the x distance you're moving, right? Where you stop minus where you began. Your y is the same thing. And what it creates is almost like an xy pair. But that xy pair is made up of a and b. It's going to be what we're going to call a and b. And from right above it, where A is your horizontal, your x's, B is your vertical component, like your y's. So we can write it, a vector now, in components if I'm given a set of points that create it. So if I want to find the component form of vector u, then u has initial point of -2, 5 and the terminal point of 3, 7. Can you give me the component form then? So remember to do this. When I draw these, like you can see up here, I can't figure out how to make them a little bit wider of a greater than, a less than type symbols. So it looks like they're just less than symbols and a greater than symbol, because that's what I'm using. But it's to denote a vector. But in this case, what's your final x value? 3. X value, final x value, that's 5 is a y value. And then minus a -2, because that's my initial. And then it's your final y value, which is 7 minus your initial y value. And you end up with, oh wait, you got to subtract a negative, you add, so you guys have 5, comma, 2. So the vector, well, not u, but v is got the component form of 5, 2. Any questions on that? Pretty simple. Given 2 points, can you find the vector? Question is, what happens if I switch those around? What if I made the initial and the terminal point switched?
2, 5.
It wouldn't be 2, 5, it would be negative 5, negative 2, because I'd be going the opposite direction. They're not the same vector because it has a different direction. They'll have the same size, right? They're opposites of each other. The next thing is the magnitude. The magnitude, guys, is the same thing as the modulus. Gives us a distance. Notice it's the same formula. The magnitude is what we call the absolute value now. And if you take the magnitude of its component form, it's just the square root of a squared plus b squared. Easy enough. I only put 2 examples on here. The third example in the book was with fractions. I think you guys should know how to square a fraction. You guys should know how to add fractions by having a common denominator. So therefore, I should not have to do those types of things. So, just to quickly go through this, the magnitude of u would equal the square root of 2 squared plus negative 3 squared, which happens to be the square root of 4 plus 9, or square root of 13. Done. Guys, this is a scalar now. The magnitude becomes a scalar because it's a number. It represents length. Distance, right? It's a length. Next one, the reason I put this one on here is just in case you have a vector that has a 0 part in its component. It's no different though. Which just ends up being what? 5. Next ones, this is no different now than if we had complex standard form. You would gather up your real numbers and gather up your imaginary numbers, right? Now, it's just saying that if you want to take things that are in component form for vectors and add them together, just add up the A's and B's. If you're going to subtract, you subtract the A's, you subtract the B's. If you have a scalar multiplication, so C is a scalar, it's a constant, times your vector, you can take that constant and move it in to all the components of your vector. Notice that C has to be a real number. Well, that's not too bad then. I don't think we're going to go through all of these, but I think we should do at least the first one and the last one. So this would be 2 times 2 negative 3 plus 3 times, oops, I forgot to change those numbers. Let's change the second one. What do you guys want to change the second one to? We need to change this. Not 30. I don't want to do 30. Let's do 5, 1. Okay. So it'll be 5, 1. And at that point, just multiply the 2 in. So you get 4, negative 6, plus 15, 3. So what this did was that number on the outside is a scalar multiplication. We are 2 times the size of the first vector, 3 times the size of the second vector, and now I can put their components together, and therefore I end up with 19, negative 3. Is everybody okay with that? I changed it because they ended up being the same thing. I didn't want the same thing. We're going to skip over part B. The part B part though, the biggest concern you're going to have is the fact that that's a minus 2. So make sure don't drop the negative, right? And then the last one, just 5 times 2 negative 3. I mean, technically we did that already, so this becomes 10 negative 15. Done. So looking at these properties of vectors, I might as well back up and say this is the properties of vectors and real numbers. Vector u plus vector v is the same thing as vector v plus vector u. That's the same thing as real numbers. It means I can add vectors in any order. Associative property? Or is that the commutative property? Commutative property. The second one is the associative property, where it means I can group them in any order I want. That's fine. If I add a 0 vector to a vector, I still get the original vector. If I add an opposite vector to a vector, you get the 0 vector. Remember, the 0 vector, guys, that actually I'll write down. The 0 vector would be that one, right? Because your A's and B's will cancel out completely. And the length of a vector, if you have the magnitude of a constant, or scalar times u, you can break it up to having their own magnitudes. So it's okay. It still works out. Also, multiplication. You can multiply a scalar in first if you want, or add the vectors first and then multiply by the scalar. It doesn't matter. Same thing. Scalars added, then multiplied to u, or a vector. Separate them to have their own magnitude, or both a vector, and then add them. That's fine. So all of these should make sense. A scale factor of 1 times u is still u. 0 times u is 0. Constant times 0 is, or the 0 vector is still 0 vector. Those are all common sense. Those are all things that you would have done with real numbers. They still apply here. So you have a section in your homework that has you make sure you can understand order operations and those types of things. And the last thing we want to talk about then is that if you have a vector AB, it can be represented with i's and j's. Most of the time, I know that when I'm going to write this in my work, I'm going to use I hat and j hat, because I can't boldface I and j on the board very well. So bring back a little bit from geotrig there. So it's I hat plus B j hat. Not that big of a deal, right? So the only thing I want you guys to do is write 5, negative 8 in terms of I hat and j hat, and then, if you could, if I gave you I hat and j hat form of vectors, can you put 2u plus 5v in terms of i's and j's? So, pretty easy. Part A just says, vector u will end up being what? 5 I hat plus, not plus, but minus 8 j hat. Easy enough. And then part B, I just want you guys to do 2 times 3 I hat plus 2 j hat plus 2 times, it's a bad 2, okay, 2 negative I hat plus 6 j hat. Distribute the 2's. Wait, is there a 2 on both of those? Oh, that was supposed to be a 5. My bad, guys. Okay, distribute the 2, distribute the 5, and gather like terms. 6 I hat plus 4 j hat plus negative 5 I hat plus 30 j hat leaves you with I hat plus 34 j hat. Done. So I don't get it mixed up with I as a complex I. And then J just makes it easier since I'm going to keep the notation the same. Any questions, guys? Homework 7.7. We'll call this day 1. Page 599. 1 through 25 odds, please. We will continue this tomorrow with more stuff. Have a great day. Enjoy the pancake run.